In experiment 4, we're going to be carrying out a Wittig reaction. In this reaction, we will react benzyl chloride with triphenylphosphine to produce what we call a phosphonium salt. We'll then react that with sodium hydroxide and trans-cinnamaldehyde to produce a diene. Now, one of the things we're going to want to determine is what is the stereochemistry of this 1,4-diphenyl butadiene that we have produced. We know the stereochemistry of the first double bond because we have that one from the trans-cinnamaldehyde. However, we don't know the stereochemistry of the second one. We'll want to determine that experimentally. In this reaction, we will use NMR and produce that. This is an error that's a copy and paste error from before, so we can disregard that those first things. Now, as a review, the way these reactions work, we're going to begin with some sort of halogen, alkyl halide, in this case benzyl chloride. And when we react this, we're going to react this with triphenylphosphine. Now, triphenylphosphine is a very good nucleophile, and so it's going to pop in and kick that chlorine off. And when this happens, we're going to end up with a species that looks like this. CH2 phenyl, or phosphorus, excuse me, that phosphorus is coupled to 3 phenyl groups. It has a net plus charge, and then the chloride gets kicked out as a minus. We refer to this species as the phosphonium salt. This species is really easy to isolate. It just falls right out of solution. We'll then take this and react it in the second step. Now, in the second step, we're going to react it with hydroxide, sodium hydroxide. That hydroxide is going to pick off one of the hydrogens next door to the positively charged phosphorus. When we do this, we're going to get a species we could draw one of two ways. We could draw it like this, or we could draw the resonance structure for this, which would be to show it like this. CH double bond P with the 3 phenyls attached. Now we can show this either way. We refer to this species as a phosphorus ylide, Y-L-I-D-E. An ylide is a compound with a positive and negative charge adjacent to each other, and we can draw the resonance structure where it's neutral. However, since carbon is much more electronegative than phosphorus, we do have more of the negative charge on the phosphorus. In the last step, we react this with our aldehyde. Now, in this case, I'm going to use the generic, although with our aldehyde, this will be a double bond and then a phenyl ring. But just to keep it simple, I'm going to use the generic. And what's going to happen is first a nucleophilic attack on the carbonyl. Now, when we get that, we're going to end up with this kind of an initial product. Excuse me, that's a little mistake there. We're going to end up with an initial product that looks like this, where we have the new carbon attached, we have the phenyl with the 3 phosphines and the plus charge, and then that carbon has the hydrogen and the other piece that we're attaching coming off, and then from there this is going to form a 4-membered ring intermediate. So we're going to end up with an intermediate that looks like this. Now, it turns out that phosphorus-oxygen bonds tend to be very strong. So simultaneously, 2 things are going to happen. One, the oxygen is going to pull this pair of electrons up here to form a double bond. And then 2, the other bond is going to come down to form a double bond to the carbon. So when it's all done, what we end up with is something that looks like this. We end up with an RCH bonded to a CH with our phenyl. Now, one of the questions that we haven't addressed here is, what's the stereochemistry? Well, that'll be interesting to see. The other product that we get out of this is triphenylphosphine oxide. The oxygen comes from the carbonyl, and then we end up with triphenylphosphine. This is a common impurity. It could show up in your NMR if you don't crystallize it out well. Okay, let's look at the nuts and bolts of carrying out this reaction. First, we're going to combine the benzyl chloride with triphenylphosphine. Benzyl chloride is toxic, so do be careful with it. Wear gloves, handle it in the hood. We're going to combine 2 mils of benzyl chloride with 6 grams of triphenylphosphine. Our solvent is going to be cumene today. And we're going to combine this and heat this. Now, in your procedure, it says to heat it for 2 hours. If you can heat it to reflux, you probably can get by for an hour. Now, what is reflux? Reflux means that the solution is actually boiling. The vapors are rising up and dripping back down. If you just heat it for an hour, it's probably not long enough. If you heat it to reflux, get it started boiling, and then start your timer, then if you run it for an hour, that should be good. Once you're done with this, you can just cool this down, cool it to room temperature, and then place it in an ice bath. Your phosphonium salt will be formed in this first step, and that will crash out. This is real easy to collect. Everyone should get a great yield from this. Take a little bit of it and set it aside for the NMR. For time's sake, we're going to need to work pretty quickly through the next couple of steps. In the next step, we're going to transfer 3.9 grams of phosphonium salt. You can do this in an Erlenmeyer flask. You can do this in a round bottom. It doesn't really matter. We're not going to be heating. We're just going to be stirring. Take your phosphonium salt, and to this, we're going to add trans-cinnamaldehyde and dichloromethane as solvent. To this mixture, we'll add 5 mils of 50% saturated aqueous sodium hydroxide. We'll then stir it at room temperature for 30 minutes. And then the reaction is done and ready to be worked up. In the workup, we will dilute with water and with dichloromethane. Last week, the aqueous layer was on the bottom. However, halogenated solvents like methylene chloride are more dense than water, and so the halogenated solvent is actually going to be on the bottom this time. I encourage you not to throw anything away until you know for sure. We'll isolate the halogenated solvent, then we'll dry it using sodium sulfate. Hopefully you remember how to do this. You should have your solution of methylene chloride. You add just a little bit of that solid sodium sulfate into the bottom, swirl it around. If you can see some particulates flowing freely, that means that you've got enough sodium sulfate in there. If everything clumps up, it's still a little bit too wet. Let it sit for about 5 or 10 minutes and then decant off the methylene chloride layer into a round bottom flask and then rotovap it down from there. In the next step, we're going to help break up the solid by triturating it. Now, triturating means to add some solvent and then stir it around. Not everything's going to dissolve, but a lot of the impurities will dissolve up. So all the sodium hydroxide will dissolve up. Now, from here, we want to get the mass, and then we're going to want to recrystallize from ethanol. And hopefully in this step, we can get rid of all of the triphenylphosphine oxide. If you are tight on time, which I think is very likely, we can do this step next week. This does not have to be done this week. We should have enough time next week to do that recrystallization and get a final NMR. Once we're all done, we'll obtain our final mass, get our melting point, and get our NMR. Finally, we're going to need to analyze our product. Now, our 2 possible products are shown here. If the double bond ends up trans, then we would say both of the double bonds have trans geometries or E geometries, and so we could refer to this as the EE product. We also could end up with the cis geometry, the trans cis, what we would call the EZ product. Now, I encourage you to think about what the spectra of these would look like. They are, because of symmetry, going to look substantially different. you should be able to tell. One of the things we're going to look for is we're going to look for the value of this splitting constant. It turns out that trans alkenes give a much larger NMR splitting than cis alkenes. Typically, a J-trans value is 12 to 18 hertz. A J-cis value is going to be between 6 and 12 hertz. That probably won't be your only clue in the NMR, but it should help you out. So get a melting point, get an NMR, and then you're good to go. Again, we probably won't get through all of this tomorrow, but if you can get a jump start, get at least the crude product isolated, that would be terrific.